afternoon, everyone. I'm Li Shuai, the Associate Vice President for Strategic Research at City University of Hong Kong. It's my great honor to have you back here to join our France-Hong Kong Distinguished Lecture Series. Okay, so let's get started. That was an informal start, okay? Now it's a formal start. So Professor Combs, President of the French Academy of Science, and Mrs. Zhu Hai, if I pronounce your last name correctly, sorry, Consul General of the France in Hong Kong and Macau, esteemed colleagues, friends, and students. I would like to welcome all of you to this France-Hong Kong Distinguished Lecture. This lecture series are a series of high-profile lectures that have been organized by City University of Hong Kong since 2005. It is our great pleasure to have your attendance here at this meaningful lecture. And today, we are very deeply honored to have Professor Françoise Combs, President of the French Academy of Science, Emeritus Professor at Collège de France, and a global leader in astrophysics, deliver a lecture titled History of the Universe. So Professor Combs is also a member of the Academia Europaea and also the NAS member in the United States. The recipient of the L'Oreal UNESCO Women in Science Award. Before I invite Professor Combs to the stage, may I invite Mrs. Christelle Zhu, Consul General of the France in Hong Kong and Macau, to give the opening speech. So, Mrs. Zhu, please.
Dear Professor Li, dear Professor Combs, distinguished participants, it is a great pleasure for me and a privilege to join you today for this new, very special edition of the France-Hong Kong Distinguished Lectures at the City University of Hong Kong, as we're celebrating the 20th anniversary. This series has, for nearly 20 years, fostered a dialogue between the world's most brilliant scientific minds. I can see many top scientists among us today, as well as students with a passion for science. Thank you very much to all of you for your presence. Of course, I would like to express again our most heartfelt gratitude to the university, to the Institute for Advanced Studies, and to our dear Professor Philippe Ziarlet for their continuous efforts to sustain this unique intellectual bridge between France and Hong Kong. Today, we are gathered to listen to Professor Françoise Combs, President of the French Academy of Science, who has traveled all the way for France for this occasion. We had the chance to hear Professor Combs last year about black holes. You are well known as a leading astrophysicist and holder of the Galaxies and Cosmology Chair at the Collège de France. Your remarkable work has deepened our understanding of the cosmos, from the hidden structure of galaxies to the forces that shape the universe itself. This year, Professor Combs' lecture, History of the Universe, will take us on an extraordinary journey through space and time, from the first seconds of the Big Bang to the accelerating expansion of the universe. It is a reminder that science, at its core, is an act of curiosity and humility, a quest to understand where we come from and how everything is connected. France has always placed science and knowledge at the heart of its identity and global engagement. From the observatories of Paris to the European Space Agency, from fundamental physics to climate science, our research community continues to explore the mysteries of our universe with one shared ambition: to better understand the world we inhabit and to act responsibly within it. Through initiatives such as France 2030, we are investing heavily in research and innovation, reaffirming that science must remain international. Collaboration with partners like Hong Kong is an essential part of this vision, one that connects people through the universal language of knowledge. I wish you all an inspiring lecture and fruitful exchanges that continue to expand our collective understanding. Thank you very much. Merci beaucoup à tous.
Thank you very much, Mrs. Zhuhao. Thank you very much for your great opening. And now, please be seated. And now, may I invite Professor Combs to deliver the France-Hong Kong Distinguished Lecture, please.
Thank you. So, dear Professor Lee and Christelle, thank you very much for your introduction, and I'm very happy to be there. So I will speak about the history of the universe, but not only from the Big Bang to now, but also I wanted to have the history of science, how all this knowledge has been accumulated. I will only go back to the 20th century because it's a birthday today. In 1925, it was realized that there were galaxies. They discovered galaxies only 100 years ago. And so I will begin there. And I will I'll try to show you how all this path was very difficult, but now it's increasing exponentially. So we have gathered a lot of knowledge, and this you will show after some slides that not only we have gathered a lot of knowledge, of course, but we have a lot discovered that we don't know anything. In fact, it's always like that in research. You discover a lot, but then, as you know, the dark matter here have halo of invisible matter that we don't know what it is. And we have discovered recently that there is 70% of the universe is in dark energy, and we don't know at all what it is. So, but last century, we did not know that we did not know. In fact, so that's funny. So first, I wanted to show you this beautiful deep field of Hubble Space Telescope. At the right, you have the Hubble Space Telescope. At the left, the James Webb Space Telescope. It's the same field. But what I want you to take over this image is that you have no star at all. It is the field of view that you see is 1/100th of the moon surface, so a very small piece of sky. But you have thousands of galaxies in this very small piece of sky, and you have no star at all. When you look in the starry night, you have plenty of points, which are stars, only stars from the Milky Way, and you don't see the galaxies, in fact. When you look in between two stars, it's what you see with a deep view of the telescope. So, and that's why we have extrapolated from these deep fields that in the horizon, I will define what is horizon, our observable universe, you have 2,000 billions of galaxies now. But you see how you can be 1% of the moon surface, you have this. Okay. So let's go in the history, how we have discovered that. Here I show the catalog of Charles Messier, you see 18th and 19th century. At the epoch, he knew that there were stars, point sources, and then nebulae. What is not point source, which are extended, it was nebulae. And he wanted to see the comet. Comet was one of the nebulae. There was Halley's comet that was discovered, and he wanted to be very famous and discovered some comets. So he looked at these 100 objects, and here are the new images from HST. So he was not looking at that. He had some white nebulae, but you see that there are very different objects here. You see real nebulae. These red are clouds where stars are forming in the Milky Way. You have some globular cluster here, which is an agglomeration of 100,000 stars in only 1 light years, while near the sun you have the first stars at 4 light years. So you see this very accumulation. So it looks like a nebulae. Of course, you have galaxies. You may recognize here Andromeda galaxy. That was called nebulae, but it was wrong. It was an error, and so on. So planetary nebulae also here. It is an envelope of a star like the sun when it will consume of its fuel and explode in a white dwarf. Okay, so here, now, there was a great debate in 1920. Are there only nebulae or galaxies? Galaxies was new. It's a world that was formed from the Milky Way. You see here, the Milky Way is a wide band that you have in the sky. and it is like milk. That's what the Milky Way. And then you have also black things, dust is absorbing the stars. But the rest of the nebulae that will become galaxies, they are called Via Lactea, like the milk is Lactea in the Latin, and they have built the word galaxy at this epoch. So there was still some people like Vesto Slipher measuring the Doppler effect of these objects. Doppler means that you can have a line, hydrogen line, which is emitting at certain frequency, and when the object is going away from you, the line is red shifted to the red. When it is coming towards you, it's blue shifted. But he noticed that all these nebulae, they were redshifted by a big amount, 2,000, 3,000 kilometers per second. So, of course, it was completely incomprehensible here, because then after some time they will have left the Milky Way with this velocity. So it was not understood at all. And one big progress was done by Henrietta Leavitt. And of course, at this, it was the beginning at the first years of the 20th century, women were accepted in the universities. And she was one of the first to have a diploma. But of course, they were not allowed to go to the telescope. It was reserved to men. So they were only confined on the underground and going to look at all the plates that were taken. And they were making this job fastidious that nobody wanted to do with a catalog of stars. There were thousands of stars. But in this work, she was very clever because she looked at some stars that are periodical. You know, the flux, the luminosity is like a sinusoid with a period of 1 or 2 months. And she noticed that in some Cepheids, what stars that are called Cepheids, there is a proportionality between the periods and the luminosity, intrinsic luminosity. There are some Cepheids that are so close that you can have the parallax and you can have the distance. So she showed that. And of course, it's very important because it's an indicator of distance. You measure this star somewhere, you have the period, and you can know the true luminosity. With the apparent luminosity, you have the distance. And she should have had the Nobel Prize, but she died before, but it's unfortunate. So other people like Hubble, who was allowed to go to the telescope, of course, and he went to Mount Wilson in California, and he tried to find this kind of Cepheids in this nebulae to see where they were. And the first one, where you know Andromeda, is a nearby spiral, and also some triangular galaxy, and 33. M is for Messier, is a catalog of Messier. And of course, he finds Cepheids there, and he concluded that the distance was 2 million light years from us. And since the Milky Way is only the diameter of 100,000 light years, it was outside. So it was an exo-galaxy, if you want. It was another galaxy. And we called for a long time, and still now, external galaxy, as if a galaxy could be internal to the Milky Way. It's not possible, but it was a language. You know, there are a lot of errors that are the tradition. And then he also found that there was a relation of proportionality between the velocity. He looked at several nearby galaxies, and they knew the velocity by Slipher, and then the distance from the Cepheids, and there was a relation of proportionality. Of course, it was very noisy at this epoch. The constant was not good. There was a factor 10, but anyway. And then he realized that the galaxies that are further from you, they are receding with a higher velocity. And he concluded in 1929, so this was a date where he concluded that there was an expansion of the universe. But for him, it was only a Doppler effect. The galaxies were really moving. The man who realized what it was the priest, a Belgian priest, Georges Lemaitre, who knew the work of Einstein. You know, in Einstein in 1915, Einstein proposed that the gravity is not a force like electromagnetic force, but it was a deformation of space. If you look at space like a 2-dimension, like a carpet, you have a ball that you put inside the carpet, you have an inflection of a carpet, and of course all the other bodies will come to the center. So this is the attraction of the gravity, okay? And then when Einstein tried to resolve this equation, the equation is a curvature of space as a function of the mass and the energy which is in space, he found that, in fact, there was only two solutions. Either the space is expanding or it's contracting. And we know that Einstein was not very happy with that. But Lemaitre concluded that it is not a Doppler effect, it's only a dilatation of space. And he called this very dense and hot early universe, it was a primitive atom. Of course, it was not the Big Bang yet, and it has taken a lot of years, you see 20 years almost. Fred Hoyle was a detractor of this. He was a very famous astronomer, making some nucleosynthesis in stars, but he was not accepting at all this expansion, and he wanted to mock that, and he said, well, there's an explosion, Big Bang, and finally the world was kept. So Einstein, in fact, tried to have a static universe, because until 1917, the expansion was known in 1929. So in 1917, he said, well, everything is fixed in the sky. You have the stars, you have galaxies. Nothing is moving, only planets, but it's a solar system. So he wanted to have a static, and there was no solution. So he had to add a constant, this famous constant, cosmological constant. It's called lambda. According to units, it's small lambda or big lambda. It's the same. Don't forget, don't search for that. But he added this, and then he had an equilibrium, a static universe, where if you take the analogy of the space, which has two dimensions, it is the surface of a sphere, and the universe is finite, static. So finite, that means if you go around this, you can go to your initial point. But it was very unstable. Like if you put a pen on its tip, of course it will fall on each side. It's not stable. There was one astronomer, De Sitter, a Dutch astronomer, who said, well, the equation of Einstein is easy to solve if there is no mass, no energy, only this lambda. And with this, he solved the equation and said, well, there is an exponential expansion. And I mentioned that because it's exactly what we have now. So he had a great intuition. He just hit the right solution. So what is now the view that we have, and it is the view of Lemaitre. That's why now the law of Hubble is called Hubble-Lemaitre. Here you have a universe which is infinite, and I choose this piece of cake to show you what is the expansion of this universe at 3 dimensions. So imagine that the piece of cake is infinite, and you have in this piece of cake, you have red points, fruits that are galaxies. Okay? So when you inflate the cake, when you cook the cake, of course it will inflate, and you see that the galaxies are not moving, but they have apparent velocity which is proportional to their distance. Okay? So it's not a Doppler effect. But why we have the impression of the Doppler effect? Because if you apply this expansion to the photon is also an electromagnetic wave. So you emit, a galaxy emits a photon which is blue, with a very high energy. And then, of course, the photon is subject to the dilatation of space. Okay? So after a while, it becomes a larger wavelength, and it is red. So this is the redshift. And very interesting to show that there's a very simple relation between the radius of the universe, the characteristic radius, with this redshift, which is a ratio of the different wavelength that you receive and the wavelength which is emitted by the object. And as soon as you measure the redshift, you measure the size of the universe at the epoch of the emission of this light. So now, at the beginning of the 20th century, there was also a revolution, the quantum mechanics. And Pauli saw, in fact, this lambda introduced by Einstein and said, well, this lambda is occupying in the equation the place of the density and the energy, but of course there is no matter, nothing. And he had the idea to apply the energy of the vacuum that they measure in the laboratory in quantum mechanics at this epoch, and say, well, maybe this lambda that Einstein has added is the energy of the vacuum. You have this energy of vacuum because of the uncertainty principle. It's not intuitive, but you have to admit it is observed, it's a fact, that when you have no particle, nothing, no energy, you have fluctuation of density. Okay, and of energy. And then he extrapolates the vacuum energy that you measure in laboratory to the universe, and then he found such a large energy. So when you look at the equation, the radius of the universe is inversional proportional to this energy. So that he concluded that the universe of Einstein was 31 kilometers. So it doesn't work at all, but we can show this because it's still there today. If we want to extrapolate the vacuum energy that you measure in the laboratory to the universe, you find something that is 100 order of magnitudes more than the energy that we measure in astronomy. So there is something that we don't know yet. It's quantum gravity. We have a lot of theory for quantum gravity, but apparently it doesn't work. So I told you that it was a hard time to convince astronomers that there was an expansion of the universe. And they were convinced in 1965 when there was a serendipitous discovery by these two engineers, Arno Penzias and Robert Wilson. They were working at Bell Laboratories, and their goal was to make telecommunications with millimeter wavelengths. Microwave between 1 millimeter and 3 millimeter is the electromagnetic wave that you have in your oven, microwave oven. And then they constructed this corn, this detector here and behind, and they tried to measure this kind of wavelength, and they were perturbed by a big noise. And the noise was not coming from the sun, because at night it was like that, not coming from the Milky Way, because when the Milky Way is down, this noise was homogeneous everywhere. And they went to the Princeton to see it was some theoretician can help them. And indeed, there was some theoretician that said, well, if there is a Big Bang with the universe which is very hot and dense, there should be a fossil radiation from the Big Bang. And then, indeed, we didn't know at this epoch at which temperature will be this Big Bang, but they measured a black body at exactly 2.73 Kelvin, which is very, very cold, and zero, it's a minus 273 degrees Celsius, so it's very, very cold, but they measured this black body, and what is impressive is that it is the biggest radiation in the universe. When you compare with the optical radiation in blue, here we have the intensity of the radiation as a function of wavelengths. So the blue is all galaxies of the universe that emit in optical. The red is a dust. When stars are formed in a cocoon of dust, then they hit the dust, and the dust is re-radiating in the infrared. So you have also a background of infrared, so it's about the same as in the optical. And then this cosmic microwave background, the CMB, is 100 times more energetic. So if you had eyes to see these wavelengths instead of seeing the optical wavelengths, then you will have a fog. You will be in the fog. It's a constant. There is no structure, well, at least for the beginning, and it is 100. So you have 400 photons coming from the Big Bang in this room per cubic centimeter. And since they are going with the velocity of light, there is about 10,000 of billions of these photons that cross you per square centimeter per second. So you are really heated by the Big Bang radiation. Now, where are these photons coming from? In fact, I make this analogy here with the sun. So you have the sun, a quiet sun without spots. And in the sun, there is a very hot matter, hydrogen, or some helium, but essentially hydrogen. But it's so hot that it is ionized. So you have a proton and electron. Okay? So there is a very tight relation between the light, the photons, and charged particles. So instead of going straight out when the photon is emitted here, instead of getting out in 2 seconds, because the radius of the sun is 2 light seconds, it takes 200,000 years to get out. Why? Because the photon is scattered by the plasma, the charged particles, and it has to go by a random walk to the frontier, the edge, and then at the edge there is no matter. It can get out, and it can get to you in a straight line. But in the center, it is completely opaque. Okay, it is exactly the same for the Big Bang. I make this image here. So in the Big Bang at the beginning of the universe, it's very hot and dense. So it's a plasma. You have electrons and protons also. And the light is trapped in this ionized plasma. And it's completely opaque. So this opaque region is the orange region that I draw here. And also I define here the horizon, the observable horizon. Why we cannot observe the whole universe? Because, in fact, the light that is coming from galaxies has sometimes to come to you. Of course, 300,000 kilometers per second appears very fast in the Earth. But for the universe, it's a slow velocity. So if you have a galaxy here, it will take 12 billion years to come to us. So when we see the photons, it's the photon that was emitted when the galaxy was very young. So you are looking back in time, and it's a way to look in the past, in fact, make the archaeology of the universe. And then when you arrive at the Big Bang, then there is no galaxy anymore. The universe is completely homogeneous, and you see the Big Bang, the last scattering surface. So all the photons, microwave photons that you see from the Big Bang comes from here, the last scattering surface. You don't go exactly to the second, but so when does it occur, this last scattering surface? It occurs when, by the expansion, the universe temperature is going to 3,000 Kelvin. And then, at this epoch, the protons and the electrons recombine to make the hydrogen neutral. So you have a neutral universe, and then the photons can go in a straight line. So you see the universe as it was. It is about 0.4 million years after the Big Bang. It's very short because the age of the universe is 13.7 billion years. Okay. So we learn a lot in looking at this fossil radiation. Here you see, of course, it's a sphere, so we make a map like in the Earth. You have to deform the map a little bit. So if I have put the whole sky, you will have a constant. So we subtract the constant. And what you see here is a dipole. It's hotter in the sense what is red and cooler blue. And why? Because the Earth, the Sun, and the galaxy in a solid motion are moving with respect to the referential frame of the universe, which is the Big Bang. So if you are running in the rain, you find more rain coming towards you than in the behind. So it's exactly this kind of thing. So we can measure our movement with respect to the universe. It's 600 kilometers per second towards a great attractor, which is a galaxy cluster somewhere. Now, if you remove the dipole, you see we are here in the longitude and latitude of the Milky Way. So you see the emission of the Milky Way, which is easy to remove also because it's not a black body radiation in the spectrum. If you have the spectrum, it's a power law. It's not a black body, so you can remove it. And then the interesting thing is the results here at the bottom. It is exactly the structure of the universe, very close to the Big Bang. And there is homogeneity. The fluctuation that you see is not noise. It's real density and overdensity and underdensity. And they are only 1 out of 100,000. So it's very homogeneous and very small fluctuation. And of course, this was the first COBE, the first satellite sent by the NASA. And we compare here all the 3 satellites that have been doing the map of the sky at this millimeter wavelength. And you see the progress here. It was not very high resolution here. WMAP has a higher resolution. And then Planck, which was launched by the European Space Agency, ESA, was the biggest resolution. It's not very interesting to go further because then the universe will smooth the resolution. So what do we get from this? In fact, you get all the parameters of the universe. It's like a fingerprint, in fact, of the universe. So we compare this map of Planck by a fingerprint. In fact, you can have several universes, and there are some constants that are from initial conditions of the universe, which are not fundamental constants. For instance, the density of matter, ordinary matter, the density of invisible matter, dark matter, the constant lambda that we see we'll have some expression for that, and the age of the universe. Also, we measure from here the curvature of the universe. Is it a positive curvature, negative curvature? In fact, we can measure that it's a flat universe. There is no curvature. And I will explain why. And what you see here is when you look at all this perturbation, you can compute the intensity as a function of the angle. Here you have 90 degrees, 0.5 degrees, and so on to 0. It's a logarithmic scale. But you see that there are some peak and secondary peak and so on. What are all these? They are acoustic oscillations. You see the point in red are the points that are observed with very small error bars, and the green line is the theory. So why is there acoustic oscillation? In fact, we know that in space, in between stars, there is no gas, well, very, very rare gas, and there is no sound in the space. But at the beginning of the universe, there was a plasma, which is very dense, and you can have pressure waves that are occurring between the matter, the ordinary matter, and the photons. In fact, the photons make a radiation pressure that prevent the matter to collapse by its own gravity. So we have this, the light and the ordinary matter are in equilibrium, and they are making some pressure oscillation that we call acoustic oscillation, okay? And this is exactly at the beginning. Here I just show a schematic increase of the radius of the universe by the expansion, and here is the Planck sky. Okay, so I said already that there are some invisible matter, and I want also to draw the history, how we have discovered this invisible matter. In fact, it's a long time ago, because it dates back to 1937. And Fritz Zwicky, which is here, it is a Swiss astronomer, but he spent all his career in California. And he was the first to realize that you need a lot of invisible matter. In this coma cluster is a gathering of thousands of galaxies in a very small volume. So it is in equilibrium. And you have Brownian motion, that is true motion this time, between galaxies. He measured this by the Doppler effect. And he tried to make an equilibrium between the kinetic energy of all these galaxies and the potential energy. And the potential is a function of the mass. And then he realized that you need a lot of mass. In terms of the mass of the sun and the light of the sun, it was a ratio 500. It's huge. You could have 1 or 2 or 5, but not 500. So there was 100 times more mass than expected. And this was a huge effect, even much bigger than error bars. So he said, well, maybe there is dark matter in galaxies, in between galaxies. He didn't know. But he also had this hypothesis that maybe the Newton law is not valid for these scales, and you can have modified gravity. But he was not followed very, very soon, because he had very good ideas, but very bad ideas also. He was not believing in the Big Bang, for instance, and so on. So there was some others, and one of them was Vera Rubin, that is now recognized by the construction of the telescope, which is called Vera Rubin. And in the 70s, 1978 and so on, she tried to measure the rotation curve of galaxies. The galaxies like Andromeda, the spiral that we have, and our own galaxy, you have disks that are rotating like the CD or whatever, and then you can measure at each radius the velocity of these stars and gas. And what you are expecting when you see the Andromeda galaxy here, when there is no matter visible here, you have no stars anymore, you expect that the curve is going down by the Kepler law, like the planets around the sun. It's expected to go down, and finally it's not going down, and what you see is the red curve. So you have to assume that there is a lot of mass that you don't see, and this is the invisible mass that we call dark matter. It's not dark, in fact. It is transparent. It is not interacting with any photons of the light. It's not absorbing, not emitting, but there may be a lot of dark matter in this room, but we'll not see it. It's transparent. So how do you, you can swallow some dark matter. How to build this rotation curve? In fact, you have a galaxy rotating like that. You see that the Doppler effect here is redshifted. Here is coming towards you, is blue shifted. You have the systemic velocity, which is the dilatation of space. And then, of course, it's rotating on one side and the other. So you fold the two, and you have this rotation curve. So it's only the Doppler effect. Okay. And now there was a small effect with the stars. When you have hydrogen, it's even more visible, this dark matter, because when I take an example, Emeritus 3, which is like the Milky Way, the optical galaxy is only in the center, in the zoom here, and all the rest is hydrogen gas, which is visible only in radio astronomy. So you had to look at other part of the spectrum. If you look only at the optical spectrum, you don't see the evidence, gravitational evidence of all the dark matter. You must see the radio, and so the radio, for instance, in our galaxy, here is the velocity as a function of radius. The sun will be there, and the end of the galaxy visible is here. But when you look at the H1, 21 centimeter is a ground state, is a hyperfine line that we have discovered only in 1951, and you see that it is really flat. It does not go down. So there is a lot of dark matter. And another wavelength that you have to see, and it has been discovered only in 1966, because you had to launch a satellite to go outside the atmosphere. The atmosphere is absorbing all the X-ray. It's just fortunate that to life exists. You will not be bombarded by X-rays. So when you look at the coma cluster with the X-ray, that you see a lot of diffuse emission. And this gas is very hot, is at 100 million degrees, very hot. Why it is very hot? Because the potential well is very deep. And of course, the kinetic energy of the particles have to be equal to the potential, which is very deep. So it's only, they are in equilibrium at this temperature, 100 million K. And when you try to know how much mass is there in this hot gas, it's 10 times the mass of galaxies. So galaxies are not the main mass of visible mass. So even Zwicky was wrong, because he see only the mass of the galaxy, which are 1/10 of the total visible mass. So at least at the beginning, when we saw that, well, we have discovered the dark matter, but it was not. It was not making the whole. It was a progress, but not the whole. Today, it remains the invisible matter, which is 5 times the visible mass. So you needed to look at all the spectrum. Now we have looked at all the spectrum, and we have still dark matter. So now we can do the map of dark matter by these gravitational lenses. You know, gravitational lenses was also predicted by Einstein, because when you have objects, background galaxies that are behind a mass like these are big galaxies in front of you, and you see that there are some arcs, blue arcs, red arcs, and so on. So these are strong lensing. That is, the gravitational lens is like an optical lens, but it makes a deformation of the background landscape. When you look at the landscape with a bottle, for instance, you see a deformation of the landscape. Here's what you see. And there is strong lensing that was discovered only some decades ago. And there is also weak lensing. Weak lensing is like that. In fact, all the image of the galaxies, when you have a big mass, let's say a galaxy cluster, and you have background galaxies, the observer is here, and you see that all the galaxies are perturbed, and you see that they are around, making some rings around the center of the lens. In fact, so with that, you can compute, in fact, the invisible matter. So the matter, you see it by the gravitational action. Okay. And now, looking to the progress again in time, in 1998, we discovered this dark energy. In fact, this lambda was introduced by Einstein, and as soon as Hubble has discovered the expansion of the universe, Einstein said, well, it was the biggest error of my life. We have to remove this constant. And this constant was taken to be 0 all the 20th century. Now, in 1998, we say, well, maybe lambda was there finally. And why? Because they do the same coup that Henrietta Leavitt said with Cepheids, to have an indicator of distance. And the Cepheids are not bright enough that you can look at the first half of the universe. So you need another indicator of distance, and this is the supernovae of type 1a. I don't enter into the details, but they are much brighter than the supernovae, which are only the end of the life of stars that explode in supernova of type 2. So these supernovae, you can see them in the first half of the universe. Sometimes you see the supernovae, you even don't see the galaxy behind. So it's really very strong. And these people, these two groups, Rees and they got the Nobel Prize with that because it was completely a revolution in our knowledge of the universe. So they established that there is a relation, exactly like for the Cepheids, you have the supernova, you have a light curve, it goes up and down, and the width of this light curve, the period of the light curve, is proportional to the luminosity, the bright luminosity. It's a universal thing. Why? Because the supernovae are lit by radioactive nickel and so on, so that's why it's always the same kind of curve. So if you observe the supernovae, you can deduce the distance of the galaxy. And then the surprise is that until this epoch, we were measuring the distance of galaxies by the law of Hubble-Lemaitre. That is, we're supposing that the expansion of the universe was decelerated, was slowed down by all the gravity in the universe. The gravity is attractive. So normally, if you have an explosion, the expansion should be slowed down by the gravity force, which is attracting, okay? And then it was, in fact, accelerating. It was a surprise. And we had to invent a component that is repulsive, not attractive. For the moment, until 1998, there was only attraction. It was only gravity. Here you have to invent something with a repulsive action. And this is the lambda, the dark energy. So dark energy, in fact, can be also some vacuum energy. I make this analogy because it's to give you an idea of the non-intuitive sign where the pressure here, the pressure of this dark energy, is a sign minus with respect to the density of this energy. When you have a gas, it is a positive. You have a pressure, the law of perfect gas. You have a pressure, which is a quantity proportional to the density of the gas, but with a positive sign, okay? So you have an idea when you have a gas into the piston like that, and you have a high pressure, the pistons get out very quickly and spontaneously because you have a pressure, positive pressure. Here, if you have only vacuum energy, like the fluctuation of the quantum energy, that is, you can create a particle, antiparticle, and suddenly in a small fraction of a second, it annihilates and makes the energy. You have to pull the piston with a lot of work, okay? You have to create all this energy. And this is why it is negative. And then it is like, in quote, a negative gravity. Of course, it does not exist, negative gravity, but you have this effect which is in the reverse sense. And it is non-intuitive at all. And that is why you can create matter from the void, in fact, vacuum. Okay, so now we are in the composition of the universe, this kind of big progress that we know what is the content of the universe, that we did not know 2 decades ago. In fact, it's only the third millennium, the 21st century, that we have this composition. Now you have 5% of ordinary matter, that is matter that we know very well, hydrogen, carbon, oxygen, and so on. You have exotic dark matter, which is not at all the normal matter. In the normal standard model of elementary particle, you have no candidates for this matter. So it's completely exotic. We don't know what is done. And you have this dark energy, which is this repulsive effect, and we don't know at all what it is, but it is 70% of the content of the universe. And of course, what I told you at the beginning, that we know a lot of things, but 95% is unknown. And it is, this composition is for today. Of course, it moves with time. At the beginning of the universe, Here you have the density of radiation, matter, or dark energy with a function of time. And you see that the matter, for instance, the matter in green, of course, the density of matter is conserved. So if you augment the volume, the density is going to 1 over r cubed, r between the radius of the universe. So you have this decrease. The radiation also is decreasing, but faster. Why? Because the number of photons is conserved also. You have a decrease in the 1 of the volume, but also the energy of each photon, as you have this redshifted, like r. So you have an 1 over r4. And that's why at the beginning, the radiation is dominating completely the components. Then you have a matter-dominated universe, and then you have a dark energy. We are here. The dark energy is dominating since 5 billion years ago. So we are entering the era where the dark energy is dominating, and in the near future, well, some billions years after that, you will be in dominating. It's the universe that was computed by William De Sitter, in 1917, a universe where only lambda is dominating. Of course, the matter is still there, but the density is becoming negligible. Okay, so you will see the fate of universe is that dominated by dark energy. Now, there are diverse possibilities there. I just make this very cartoon just to show you where we are. We are in the plane here, and the time is here. The Big Bang is this, and here the future is in blue. We are here, and we are observing only the past, of course. We are trying to predict the future. And in 1998, we were in this model, a very simple expansion, and there were still some problems because you see here that the Big Bang was too close to us. The age of the universe was too small, and we could observe very old stars in the Milky Way that were older than the universe. So there were some problems. Now, with the lambda, with discovery of lambda, it solves many problems because you see that we have now an age of the universe which is larger. We have 14 billion years. Then we don't find any stars that are older than the universe. So, okay, this is a good fact. Now we can all the observation until now gives you this curve in red. So you have the Big Bang, you have an expansion. Then it is deceleration because the gravity is slowing down the expansion, and then the dark energy is dominating from this period here. And then we are here. Of course, we don't know. We certainly are not in this possibility of big crunch, sure. And we are not really in this big rip. Maybe you have seen in the science fiction books that people are saying that there will be a big rip and so on. I think it's not realistic at all. It's only science fiction because the density will not be conserved, or the matter will not be conserved. So here we are in this part here where, for the moment, it looks like a cosmological constant. Now we want to know better because we have not enough precision. So how we do that? We have to observe many, many galaxies. And I come back to these acoustic oscillations. I described that at the beginning, the matter was in equilibrium with the photons, and there was oscillations. When the photons were decoupled from the matter, then this structure of oscillation remained frozen in the matter. So in the matter, you have a ruler that is only giving you the expansion of the universe. Okay, so this ruler is here at some epochs. If there is an expansion, the inflation of space, then you can measure this ruler. So you have to determine this structure, which is a faint structure that remains in the stars. And that's why a lot of projects now are doing that. And I show you the recent, maybe you have heard in the press, that people are finding some preliminary results with this survey of galaxies made with this telescope, which is in Chile. It's a dark energy spectroscopic instrument dedicated to the dark energy nature. And what they do is that they have 1 million of galaxies where they measure the spectra. They have 40 million spectra in a few years. And they try to have the best 3D map of the universe and to show this structure of a baryonic acoustic oscillation. And how they can do that? In fact, they have, at the focal plane of their telescope, they have 5,000 robots. You see this point are robots. I make the zoom on this. Each is a little motor, and they make an image of the sky. They know where the galaxies are, and then in a few seconds, they can move the fiber. They have an optical fiber, and they move the fiber to the galaxy, and then they can make, in a pause of 1,000 seconds, they can have 5,000 spectra. So each night they have 1,000 spectra. That's why they can have millions, 40 million spectra in 5 years only. But 100 millions, it's not enough, in fact. What they are doing, in fact, they are measuring the structure, this ruler. I put a ruler. So they measure this ruler, and they measure like this the expansion of the universe, the radius of the universe. And is it slowing down, expanding, and so on? We don't know exactly with precision. And what the results of their study is that maybe it is not a constant. It is a dynamic energy, which means that there is a fifth element that we call the quintessence. And so it is preliminary, and we have to wait for Euclid. In fact, Euclid is a satellite that has been launched by the European Space Agency again. And this is a space telescope like HST and James Webb that I've shown you. But the HST and James Webb make very, very small, deep field of view, so they have not mapped all the sky. Euclid will map all the sky, and will have 12 billion galaxies, so 1,000 times more than DAISY. So we'll have much more statistics, and we'll have exactly the precision of what is the dark energy, and is it a constant, is it a quintessence, and so on. So we'll learn a lot of fundamental physics. So in the 5 minutes that remains, I will show you, I'll try to show you something else about what is, now it is speculation. For the moment, it was established facts. The Big Bang is not a theory, we see the Big Bang. But now I just try to show you what is just at the beginning of the Big Bang. I replot this figure that I've shown you already of the horizon. And the radius of the horizon is the path that has been run by light from the Big Bang to today. So today is for 14 billion years. But when you look at this map of Planck, which is done at 0.4 millions and not billions of years, the horizon was only very small. It was only millions of light years. So here, the horizon is 1 degree. So in this map, you have 40,000 horizon. 40,000 horizon. But the horizon is such that they are independent. The light cannot go faster than the velocity of light, so they are completely independent. So the big problem of the horizon is that you see all this at exactly the same temperature as a precision of 1 out of 100,000, okay? It's exactly the same temperature, while they have no way to make a concertation that you should be at this temperature or not. So this is a big problem. It's unsolved unless you have inflation. And if you have inflation, it is this kind of a diagram here. In a very small time, 10 to the minus 32 seconds, you have an inflation by 10 to the 30. So it's big. So it's very speculative, but I must say that it's the only theory that works for now. So you can gain, in fact, from the light. The light has no time. Here I plot the horizon, you see, and if you inflate this by inflation, you have a big universe, and the horizon is the same. In 10 to the minus 32 seconds, the light has not time to move. So that's why you can have, in this space, you can have plenty of horizon, okay? So you come from the same part of the space, in fact, that has been inflated. But then you can solve, by this inflation, you can solve two problems. First, why our universe is flat, even if normally, if it is very small at the beginning, the curvature, it should increase with time, and it is not. And why? Because, in fact, if it was curved, you see here that you inflate the sphere, it becomes flat because you are in the tangential plane. So the idea is that it is exactly what we have. We are, all the horizon, observable horizon, is on the tangential plane of a certain curved universe. And also, it gives you the origin of the fluctuations that we see in the Planck map, because we have fluctuation where they are coming from. In fact, they could come from the quantum fluctuation that you are in the vacuum, because, of course, they are very small. In general, they are 10 to the minus 35 centimeter. And then if you inflate by this factor, it will become centimeter-like, and it is macroscopic. And then you can explain why you have a primordial fluctuation and so on. And the spectrum of fluctuation works very well with this view. So you imagine that there is a vacuum, energy of vacuum at the beginning, and after this inflation, then you can have structures that are precipitating at some point. But of course, there is some drawback. There are 3 advantages, but one drawback is that you could have several universes. And there is no way that you can stop inflation in all the universe, which is infinite at some time. So you have several regions of the universe where you will materialize your vacuum energy in some universe that will create the matter, but not in the others. Of course, you will never see able to see the other universe, but this is exactly the view that was derived in 1981 already by André Linde, because this theory of inflation was created by Alan Guth in the States and André Linde in Russia, and it was 1981. They realized that, and since 1981, we have no better theory. So it's a longevity in this theory. So what we interpret, that we are in such universe, like maybe the green one, we are exactly in the tangential point here, and we don't know how small, because we have only the horizon, we see only a part of it, and there are an infinity of multiverse. So this is a possibility, and I finish here. The history is not over, as you see. There are plenty of things that are unknown. We don't know 95% of the content of the universe. We don't know if there are several universes, and we could detect and confirm the inflation by these primordial gravitational waves, because here, when there is a big inflation, it's a perturbation of the space that makes some gravitational waves of the space, and we know which kind of wavelength, and we hope that we will be able to measure these gravitational waves with the pulsars. There's a pulsars timing array that are functioning now and able to see nanohertz in the frequency of these waves, and maybe in 10 years from now we'll confirm or infirm the inflation. So I stop here. Thank you.
Thank you very much, Professor Combs. Now I'd like to open the floor for questions.
Yes.
Yeah. Just press the button in front of you and then you can speak. Yes.
Thank you for such a beautiful lecture. When you mentioned these numbers like 10 to the power 30 or 10 to the minus,
Yes.
are these, do they come from experiments or from numerical simulation of some equations?
No, it comes from the constraint that we want, that this structure becomes centimeter-like after this. Well, it comes from the size of the universe with respect to the horizon. When you see the fossil radiation of the Big Bang by Planck, you know that there's 40,000 universe. So you know that at which speed you have to gain to see that all this universe come from the same part of the universe at the beginning. So this gives you the size.
So it's from observation?
Yes.
Yes. Okay.
If you believe that it is the right theory, it's from observation.
Yes. Thank you.
Thank you. Any other questions? We had earlier a question from here.
I think it was a very comprehensive and exciting talk. Can you tell us a little bit more about inflation? something that happens in 10 to the minus 32 seconds and in inflation by 10 to the 30th.
Yes.
How are the energetics? How can we think about it? Because you showed the diagram where actually there are different spaces and they touch. Is it that all of a sudden, how can you increase the volume so dramatically in such a short time? It's just a change in space that, that reconfigures that volume?
Yes, in fact, it's a big question and it's not intuitive. There is an inflaton. We are obliged to create a scalar field, inflaton. And this is a field which is rolling in, it is not at equilibrium. So we are a metastable, in fact. So it is not in equilibrium. So after a while, it rolls to equilibrium very slowly. It has to be slow. And then it's like metastable when you have a lake, which is below, and then you have suddenly some horses that try to, and then all of a sudden it becomes ice. It's a metastable things, and we have to invent this, in fact. But it's come from the particle physics, astroparticle theory, where you have such kind of phenomena of metastable and out of equilibrium things. So the vacuum is, the false vacuum is completely out of equilibrium, and suddenly it comes to equilibrium, and then it forms. And why we form, we are able to find energy and then matter afterwards. But at the beginning, it's energy, and then you form particles and antiparticles, and then it goes down and form particles. Because of this minus sign is exactly the same thing, then the dark energy, the pressure is negative with respect to the density. So in inflating, you gain energy. It's a reverse than in the pump. When you push, it heats, so it's the reverse, in fact. So you gain energy just in this expansion. So that's why you can create the matter, you can create the universe.
Oh, wonderful. Yeah.
You did not talk about black holes in your talk.
There is nothing, well, I talked about black hole last year.
Yes.
But black hole, they are going black, but it's completely different. Black holes are very well known with respect to what I've said there. Black hole is really, it has been predicted by many people, even before Einstein, there was Laplace and so on. Yeah. And we are convinced that black hole exists since 1975. 65, sorry, because we have seen them. Yeah. We have seen stars that are rotating in invisible aster, and then we can measure the mass and see that it's a black hole. In the center of the galaxy, the supermassive black hole. All is very well known now.
Yeah, it's well known, but still there is a lot of observations. So what the people who do these observations, do they try to answer some questions which are related to the one you are asking today?
Yes, possible, because you are thinking about the gravity, and yes, but in fact, when you are thinking of dark matter, you need modified gravity in weak field. Mm-hmm. In strong field, the same Einstein works very well. So you are going to the outer parts of galaxies where the field is weak, and the black hole is a reverse, it's strong field. So it's completely different, in fact. For dark matter, maybe for quantum gravity, yes. Mm. So then you can have this holographic gravity and so on. But it is only to solve the quantum gravity. You know that cosmic strings, well, the string theory doesn't work. Cosmic string also don't work at all. But we are looking at a new theory of gravity, so maybe the loop gravity or whatever. But for instance, nothing works very well.
Okay, thank you.
We had a question here. Can we go here first? Yeah. Because I know he has been waiting for
I have a naive question that how are the dark matter distributed in the universe? It seems it's all concentrated on the galaxy, right?
Yes,
but
dark matter
why is that?
It's following the galaxies and the cluster of galaxies, and in the voids, because in between clusters of galaxies you have voids, there is no dark matter. So dark matter is attracted, there is gravity. So in general, it is not in the center of galaxies, because to go to the center, you need a dissipation. So only gas can come. So dark matter halos are in variable equilibrium, so they form by the fluctuation that we see in the Planck. They form halos, they collapse, and then when they are virialized, they stop there like that. They don't go to a very high concentration. So in the center of the Milky Way, there is no dark matter, because there is only the gas that can dissipate, radiates, and away. The dark matter doesn't radiate. So you have halos that are virialized, but you have no concentration. But still, you have something which is associated, because in fact, I've not had time to say, but at the beginning, if there was only the ordinary matter, you will not form galaxies, because you have to wait that the photons are decoupled from the matter, and then it is too late. The expansion will prevent the collapse. Now, the dark matter is very useful because it is not interacting with the photons, so it makes potential wells, it collapses, makes potential wells, well before the ordinary matter can fall in the potential wells. So you form dark galaxies first, and then when the photons are decoupled from the matter, the ordinary matter will fall in the dark galaxies, and then the gas will go to the center, form stars, and so on. So the dark matter halos are formed before galaxies.
Is there a theory about how large the size of the dark
all
matter
sizes.
on the all sizes?
When you make
galaxies?
a simulation with cold dark matter, I have not described all the models of dark matter, but the main one is cold dark matter. Then there is size from the size of the Earth, can be an Earth size of dark matter, to the big supercluster that are not completely virialized yet, and they will never because of the expansion accelerating. But the clusters are dark matter halos also, so all sizes dark matter.
Oh, that's cool. Now we go back here.
Yeah. Yes, while we, of course, know what is normal matter, and now we have explained also, and we can accept the idea of this dark matter by theory, experiment, and so on, but I'm a bit lost with the exotic matter. Can you, which accounts for 25%?
Exotic means that we don't know at all what it is not. There's no candidate in the normal matter, which is quarks, leptons, neutrinos, and so on. It's not this. Why? Because all this matter is interacting with light, with the electromagnetic force.
Yeah.
exotic,
That's how it is defined, but...
Exactly. The exotic matter does not interact with the electromagnetic force. So it's exotic because all the matter we know is interact with the electromagnetic force. Here we don't know, and we assume, and the best candidate of dark matter was assumed to be a weak WIMPs, weakly interacting matter particle. Weak was with a weak force, the weak nuclear force. And then with nuclear force, we had the idea that it has, well, these dark matter particles are neutral, of course, because if it was ionized, it will interact with the photon, so it is neutral. And the antiparticle is the same. So these particles annihilate at the beginning, and then with inflation of the universe, there is a certain time where they are decoupled, that is, there is not enough density of the dark matter to be annihilated. So there is a relic density, and this relic density was exactly, if the dark matter was 100 times the mass of the protons, it was exactly what we need for the dark matter. But now we have looked at the accelerator of the CERN, for instance. We have been able to create this particle by collision protons and so on. We have reached 100 times the mass of the protons and even 10 times more. Nothing has been discovered. There was the supersymmetry and so on. There's no supersymmetric particle, and all these have collapsed. And now there is other candidates like axions, sterile neutrinos, but also modified gravity.
Hi, thank you. Do you think the question is, do you think the lambda CDM can explain the high redshift massive galaxies and the supermassive black hole, the little red dots, or do we need something else?
Yes, it's a very good question. That's a question that we are trying to solve nowadays with the James Webb that have shown a lot of massive galaxies and massive black holes. In fact, it's possible because it's nonlinear physics, and you have a lot of feedback effects when you form stars. You have supernovae that can push the stars. You can have no feedback, a lot of feedback, so you can turn some buttons to fit what you want. So people are trying to to turn a lot of buttons. For instance, when you have a black hole in the center, you have a lot of energy, and then you can also regulate the star formation. You can prevent the black hole to make this feedback, so you have more massive galaxies and so on. So people are trying. They don't succeed for the moment, but there is hope that with turning a little bit the parameters, they will succeed to form this. If not, then there is a solution about modified gravity, because in modified gravity, you form massive galaxies at the beginning. You have no dark matter, and you have a boost. In the beginning, you have a weak field because all the universe is homogeneous. So the gravity between particles is very, very zero. So you have a very weak gravity. And then you have a boost of gravity due to the modified gravity. And then you can have many more massive galaxies early on. But maybe it's a hypothesis that would be infirmed speculation.
Great. Any other questions? Okay. Thank you very much, Professor Combe, for the intriguing discussions. Thank you all for the lovely questions. May I invite you to remain on the stage? Before we end the lecture formally, may I invite the distinguished guest today, Mrs. Joelle, and then Professor Charlotte, to come up on the stage, and also Professor Cheng, please, to come up on the stage to take a group photo.